Okay, welcome back. Hopefully you had a relaxing Thanksgiving and are recharged for the stretch run. We only have two more classes, so today and Thursday. The last day of class is Monday, but obviously we don't meet on Mondays. So make sure you keep attending classes until Monday. Um, Next week, you should be preparing for finals. You might have some finals in other classes. Um, I will stop having evening office hours after classes are over, but I will be available during class time to meet. So I'll be online. I'll send out an announcement with that information. So I'll be able to meet. You'll be able to meet with me. You know, this week during office hours, next week during class time, and then our final exam is Friday, December 10th. So a week from Friday, 8 a.m. I will send out a Canvas announcement with all that information as well, but it'll be here at 8 a.m. And as I've mentioned before, you'll be retaking your three lowest quizzes. So that means the individual chapter quizzes, not the group extra credit quizzes. But if you just look at your grade book, find the three lowest chapter quizzes and study those, because those will be the ones you'll be retaking to get a better grade. If you are comfortable with the grade you have, you don't need to come to the final. It can only improve your grade. Your grade can't go down. Okay. So I'm happy to discuss, if you have questions about what your grade is or what would be the effect of taking the final or not, I'm happy to discuss that with you. And we have one last quiz, chapter 16 quiz, which we may do today. I think we're probably going to push it off until Thursday, just based on the amount of stuff we have to cover today. Yep. Yeah, so Canvas does not yet have your lab grade included. Um, I have an assignment created for 15% of your grade for lab. Um, can you enter like a place? Are you saying that you can't enter a trial grade there to see what effect it has on your overall score? I might not have published it. I don't know if you, maybe it has to be published before you can do that. I'll look into it. Um, but basically, you can look at your grade, and that's 85. What is on Canvas is 85% of your grade. So if you have a sense of what your lab grade will be, you can do the math and figure out what that average will be. I'll try to make it as easy as possible. I don't have the student view on Canvas, so it's sometimes hard for me to know what you can see and what you can do. But I will post your lab grade scores as soon as I have all of them reported. So your individual instructor may have submitted their lab grades, but until every instructor has submitted them, I'm not going to go through and type them in. Um, Hopefully that'll happen before the final, so you know exactly where you stand. Any other questions, like administrative stuff, end of semester? All right. I bought a 30 pack of masks and put it in my office at the beginning of the semester. Um, and this is class 28. We have 29 classes plus the final, and my stack of masks is getting very, very small. So counting down. Um, we were talking about electromagnetic radiation as a consequence of Maxwell's laws, which were just Gauss's laws for electricity and magnetism, Ampere's law, Faraday's law with Maxwell's correction, brought together into this unified theory of electromagnetism that we call Maxwell's laws or Maxwell's theory. And the consequence was it gives rise to electromagnetic waves. And so we talked a little bit about how we represent waves, and we're primarily going to talk about or represent the electric field associated with the traveling electromagnetic wave, with the understanding that the magnetic field is proportional to this. So if we wanted to write a complementary magnetic field, we would just take this and divide it by the speed of the wave to get an expression for the magnetic field. And the direction of the magnetic field is related to the direction of the electric field through the cross product. E cross B gives us the direction of propagation. So we're going to describe that a little more quantitatively today by introducing something called Poynting's vector. But first, let's go through this expression for an electric field. This is a fairly generic way to write an expression for the electric field. There's other ways to do it. But let's talk about what all these parameters mean. We introduced them last time, but it's a good review. So what we see is some vector times a cosine function. Could be sine. Here it's written as cosine. And the arguments of that cosine have a factor that depends on position, in this case x, but it could be y or z or any spatial coordinate, and also a factor that depends on time. And then it has a value called the initial phase that represents the value of this cosine function when x and t are 0. So if it's not starting at a maximum at x equals 0 and t equals 0, we can account for that by having some initial phase here. And so clearly when this first term increases by 2 pi, our cosine has to repeat itself. And so we say that as x increases by an amount that makes this term go up by 2 pi, the wave goes through one full cycle, and that distance over which that occurs is called a wavelength. And that tells us that k, this factor in front of the x, must be 2 pi over a wavelength, so that when x increases by a wavelength, kx increases by 2 pi. Now this omega, we know that is the angular frequency. It's the number of radians per second. And here it's just the factor in front of time. So likewise, when the time increases by 1 period, the length of time it takes the wave to oscillate through one full cycle, this argument has to go up by 2 pi. Therefore, we can say omega is 2 pi over the period, or equivalently 2 pi times the frequency, the linear frequency. Okay, so little f, we call the frequency of the wave. It's measured in hertz, or cycles per second. Omega is called the angular frequency, and it's measured in radians per second. So the number of cycles per second, f, the number of hertz, is inversely proportional to the time. So if a wave has 1 million cycles per second, then it takes 1/millionth of a second for one cycle. So those are inverse relationships, and they're related to omega, because when the time increases by a period, this omega t has to increase by 2 pi for the argument to go up by 2 pi and this cosine function to repeat itself. So if you keep that idea in mind, you can work out the relationship between these quantities, omega, k, lambda, and period, without having to necessarily memorize all these relationships. And then finally, the speed of this wave and the direction of the wave, we can work out from the parameters in this argument here. So we know that if we want to follow a point on the wave, as if we're surfing the wave, if you imagine a surfer, as they move along the wave, they're staying at a certain height on the wavefront. So as they move along, the rate at which they move is the rate at which a point on the wavefront moves. And a point on the wavefront is a point where this argument is constant. Okay, so for example, the peak of the wave occurs where this argument equals 0, right? Because then cosine of 0 is 1. We have a maximum value for our wave. So if time goes up, which is what we have when we follow something in time, we would need x to go down in order for this argument to remain 0 if it started out as 0. And that is to say that this represents a wave traveling in the minus x direction. And furthermore, if time increases by 1 second, the amount that x would have to go down would equal omega over k times 1 second, just for this sum to remain 0. So the speed of the wave is omega over k. And the direction we can find, again, from considering this argument and thinking about what happens when time increases. What does x have to do for the sum of these terms to remain constant? And here it has to go down because the sign of this kx term and the sign of this omega t term are opposite. So if the signs are opposite, then this represents a wave propagating in whatever direction this spatial coordinate is. Here it's x. Could be written in terms of y or z or some combination. If the signs are the same, then it's a wave propagating in the negative direction. Because as time goes up, if they have the same sign, the term with the spatial coordinate would have to go down. Okay, so we can get the direction by inspecting this argument. Finally, the polarization, the direction of the electric field, is given by the direction of this amplitude vector, E naught. Okay, so that has that's a vector. It has a direction associated with it, and the wave is just going to oscillate in whatever direction that is. Okay, so the speed of the wave is given by omega over k, and when we actually derived the wave equation from Maxwell's equations, we saw that omega over k was 1 over the square root of epsilon mu. Okay, so in a material, the speed is related to the material properties epsilon and mu. Remember, epsilon was the permittivity of the material. It's related to the dielectric constant, or how much material polarization we get when we apply electric field to it. And mu was the permeability of the material. It tells us about the strength of a magnetic field produced by a current. And if we're in vacuum, of course, these numbers are known. They're constants. We use epsilon naught and mu naught. And in vacuum, that gives us a constant for the speed, which we call c, the speed of light. Okay, so that's a physical constant. But if you're not in vacuum, then the speed will tend to be slower. It's always slower because epsilon and mu can only be bigger than or equal to epsilon naught and mu naught. Remember when we had dielectric constants in a capacitor, they could only increase the capacitance. They could never decrease it. So epsilon is always greater than or equal to epsilon naught. So the speed in any material is always less than or equal to c. And the amount that it's smaller than c, we call the index of refraction, n. So this is something, a parameter that's really important in optics. And if you go on to take Physics 52, which is basically light and thermo, you'll deal with the index of refraction of materials quite a bit. They tell us about how light bends when it goes from, say, air to glass or air to water. We can use the relationships that rely on the index of refraction to derive how lenses focus light, how we get refraction at an interface, all sorts of useful things. For our purposes, n is just a number that represents this ratio, and since the speed in a material is always less than the speed of light, then n is always greater than 1. Or it can be equal to 1 as well. In a vacuum, n would be 1, but in a material, it's generally greater than 1. So for example, in glass, n is 1.5, typically. So the speed of light in glass is about 2 times 10 to the 8 meters per second instead of 3 times 10 to the 8 meters per second. Okay, so light or other electromagnetic waves have energy associated with them. It takes energy to create a wave, and that wave can transmit energy. So we know this because when you plug in a light bulb, it takes energy to illuminate it. And if you put out a solar panel, it can gather energy from the sunlight that you could use, for example, in your house or to power your calculator or whatever it is. We know from our work on capacitors, way back in chapter whatever, that there's an energy associated with the electric field between the plates of a capacitor. And we found that energy density to be 1/2 epsilon E squared. So we can find the electric field in a capacitor from the voltage and the distance between the plates. But just in general, any electric field has some potential energy associated with it. And this is a potential energy per unit volume. So if you have a field over a larger volume, it stores more energy, but this is the density of that energy. Likewise, we derived an expression for the magnetic field when we dealt with inductors and found that the potential energy per unit volume for a magnetic field of magnitude B was 1 over 2 mu times B squared. So knowing that the electric field is related to the magnetic field amplitude by a constant of proportionality that equals the speed of the wave. I've written it as c here, and in vacuum it's c, but in general that would be the whatever velocity you have in the material that you're in. We can say that the total energy density is the energy density in the magnetic field plus the energy density in the electric field. And because our wave has both of those, we will add them up to get the total energy density in the wave. And now we can replace the magnitude of the magnetic field B with E over C, which I've done here. And because B was squared, I end up with a C squared in the denominator. And if we go back to the previous slide, C, the speed of light, is like 1 over the square root of epsilon mu. So in vacuum, it's 1 over square root of epsilon naught mu naught. So C squared in the denominator is equivalent to having an epsilon naught mu naught in the numerator. So the mu's cancel, and both these terms then look like epsilon over 2 times E squared. And if I add up half epsilon E squared plus half epsilon E squared, I get a total energy density of epsilon E squared. So epsilon is the permittivity of the material, E is the strength of the electric field in a traveling electromagnetic wave, and we find that the energy density is proportional to the field amplitude squared. So it's a pretty simple result that we get when we go through our results from the electric and magnetic field separately. And of course, this is the total energy. Even though it's written in terms of the electric field amplitude, it's really the sum of the electric and magnetic field. It's just we're simplifying it so that we can write it in terms of just one of those things. Now, the potential energy in this wave shows up when we look at it. If this is light, it can stimulate the rods and cones in our eyes and produce a visible response. But one thing that that is sort of beyond the scope of this class, but is kind of interesting, is that the response of your eye is not uniform. So we talk about the visible range of wavelengths being about 400 nanometers to 700 or 750 nanometers. But your response varies considerably among that. So I wanted to just demonstrate that. And so I'm going to point the camera at the wall, and I'm going to start with a green laser pointer. This is a 1 milliwatt laser pointer. You can see it on the wall, or you can see it displayed on the screen. And just visualize or think about how bright that looks. And let's compare that to a red laser pointer that is the exact same power. Which one looks brighter? The green one looks considerably brighter. And that's because your eye's sensitivity peaks in the green to yellow, right sort of in the middle of the visible spectrum. And the red is further towards the edge of that visible spectrum, so your eye's not as sensitive. Now here's a laser pointer that's 100 times more powerful, but it's at 405 nanometers, which is violet. This is the laser diode that would be in like a Blu-ray player. Let's look at how bright this appears. So you can barely see that, at least relative to the green one. The violet one appears much dimmer, but it's actually about 100 times brighter in terms of the actual power. Your eye's just not as good at detecting that violet light. So there's energy in those waves, but our ability to sense that is affected by the spectral response of our eye. So the way that we describe the energy in a wave is usually not in terms of the total amount of energy, but the energy per unit area. Because this is what is important when light hits our eye, for example. The size of our eye, our pupil, which can change. At night it expands, it dilates to let in more light, and during the day it contracts. But whatever that size of that aperture, that determines how much power gets into our eye. So a bigger aperture will let in more light and more power. So we want to be able to describe the light in terms of not the total power, but the power per unit area. So that when we then let a certain area through an aperture or onto a detector, we can calculate then the total amount of power we're detecting. So that power per unit area we call the irradiance. So from the word radiate, or transfer of energy through a wave, the irradiance is the power per unit area. Power is just energy per unit time. So let's say the potential energy is the energy density that we just derived times the volume of our the region where we're considering the energy being stored. Okay, so the energy density was epsilon E squared. And if we consider light passing through some aperture of area A, that might be the pupil of your eye, or it might be the size of a solar panel of area A that's collecting a certain irradiance and turning it into power that we can use. So if we have that aperture and light coming in perpendicular to that, and over a time dt, if it's moving at a speed of v, the amount of light, or the volume of light that passes through, has a depth of v times dt. So essentially, this little box here represents the volume of light that passed through that aperture in some time dt. So that's the volume that we're going to use over here for delta V. It's just A, the area of the side, times V dt, the thickness of that box that gets let through in that amount of time. And now we're going to use that the velocity is 1 over the square root of epsilon mu. So we replace the V with epsilon mu. And we're looking for the power per unit area. So power is energy per unit time. And we're going to divide that by the area. We're going to give it this letter S for the moment. We also sometimes call this I. The irradiance is I. The Poynting vector that we'll introduce is S. But here I'm calling it S. So we want 1 over A times du dt. So we have an expression for u that has a dt in it. So when we divide it by dt, that cancels out. The A cancels out. And what we're left with when we replace the v with 1 over square root of epsilon mu is here. And you can see that we can write this in a variety of ways. This 1 over epsilon mu is a velocity. If you want, we could bring the epsilon into the square root and then cancel those out and write this as square root of epsilon over mu times e squared. But the point is, the power per unit area depends on the electric field squared, just as the energy density did, with different factors out in front that give us a power per unit area instead of an energy density. Okay, so the irradiance is the average value of this. So we know that the electric field is oscillating. It's going between a maximum value and a minimum value, which means E squared goes between a maximum value and 0 and back to a maximum value. So the average value of this expression, which is really what we care about, because if we have something like our eye that's detecting an optical wave oscillates 10 to the 13 times per second. Our eye can't see changes that fast. What we see is the average power. So if we want to average this, it averages out to 1/2 of this peak value. We get that by using the root mean square value for the electric field, which is E naught over square root of 2. When we square it, that gives us this 1/2. And here is written in terms of not the speed v, but c over n. Remember, n is the ratio of the speed in a vacuum to the speed in a material. And so this is the form that we typically use to write the average power per unit area, what we call the irradiance. And that's a useful term, because if you know the irradiance of a wave and you know the size of a detector, you can calculate the power being detected by that, whether it's your eye, a photodetector, a solar panel, whatever it is. So that irradiance is related to a vector called the Poynting vector, which is a vector that has a magnitude equal to the power per unit area of the wave and a direction in the direction of propagation. So it's convenient that it's called the Poynting vector because it points in the direction that the wave is propagating. But it's spelled a little differently. This was John Henry Poynting. He was a student of Maxwell who came up with this theory of electromagnetic radiation. And Poynting worked out the energy flow in a wave. And so he gets his name associated with this vector. But I like to think about it as the direction that the wave is pointing is the direction of this vector. So its magnitude, we just worked it out, is the power per unit area epsilon v times E squared. This is not an average. This is the instantaneous power per unit area. And we know that that's oscillating between a max and 0 very rapidly. And the way we tend to write this is we separate this E squared into E and V times B, right? Because E is V times B. And then this V squared times epsilon we can write as 1 over mu, because V squared is 1 over epsilon mu. So the magnitude is EB over mu. And in order to get the direction, we know the wave propagates in the direction of E cross B. So we can write this pointing vector as 1 over mu times E cross B. So this will be a vector that, because it's E cross B, points in the direction of propagation of the wave. And because we've got this 1 over mu in here, and we've worked out that that gives us the power per unit area of the wave, this vector, the pointing vector, is the power per unit area of a wave in the direction of propagation. Does anybody watch Veritasium videos on YouTube? You should. They're good. They're interesting. A lot of physics stuff in there. There's just one last week, I think 4 or 5 days ago, talking about the pointing vector and how, as a result of the pointing vector, you can think about energy propagating not through wires in a circuit, but actually in the field around the wires. It's kind of interesting. There's a few mistakes in it, but it's worth checking out. It's called Veritasium, and just check out their latest video. The energy in the wave can be used to power things if it's converted into electrical energy by something like a solar panel or other diode-based semiconductor. But the wave also has pressure associated with it. It can exert a force on something. And so we know from mechanics that potential energy is related to force, in the sense that force is minus the gradient of potential energy. Said another way, potential energy is the integral of force times distance. Right? Work was force times distance. Work is a form of energy, or a transfer of energy. So potential energy is minus the gradient of potential energy. And we also know force is pressure times area. And so if we put these things together, we can say that pressure is the force that something exerts divided by the area over which it exerts it. And the force from an electromagnetic wave is related to the potential energy in that wave. So the gradient of potential energy is, let's say, a wave propagating the x direction would be du dx. So du dx would be the magnitude of the force that a wave could exert, and area is the area over which it's spread. And if we write that potential energy as the irradiance times the area times time, so remember, irradiance times area is some power, and we multiply it by time, we get an energy. Then we can recognize that the irradiance doesn't depend on x if we have a plane wave. If we have a wave that's propagating without spreading out and changing its potential energy, then we can bring this outside of this derivative, and the areas cancel out, and we're left with dt over dx, which is 1 over the speed. And so we get the pressure of a wave is its irradiance divided by its speed. Okay, so we don't really think about a wave as being able to exert pressure. We don't feel a pressure from the light acting on us. It's there, it's just very small. So it's typically negligible compared to the other forces that we feel, just from wind. I mean, the reason we don't get pushed over is because there's air molecules on the other side of us pushing back. But if we were to go out into space, and we were to take a large reflective surface and expose it to the sun, the sunlight hitting and reflecting off of that surface will transfer energy to the surface. Actually, it will transfer momentum and give us a kick. And so there are satellites that use this radiation pressure force both to orient themselves or to propel themselves. So there's one called the Solar Sail Project. It's attempting to raise its orbit by using radiation pressure. It's a very small force, but it acts over a long period of time. So unlike a rocket propellant that you burn up the fuel over the course of a few minutes, and then you no longer have any fuel left to propel your spacecraft, the radiation pressure is continuous. And it's been used as a sort of clever way to keep spacecraft stable. So normally they have these gyros that measure their rotation, and then these reaction control wheels. If you spin the wheel, it causes the spacecraft to get a torque in the opposite direction. So by spinning these reaction control wheels, it can orient the spacecraft, keep it stable in a particular orientation. These reaction control wheels fail every few years. Their lifetime is only a few years. So you have spacecraft that are in space for dozens of years, and after 4 or 5 years, the reaction control wheels have failed. So this famously happened on the Hubble Space Telescope, needed to be repaired by a spacewalk where they replaced the reaction control wheels. More recently, it happened when the satellite was not able to be serviced. And so without any reaction control wheel to steady the spacecraft, there's nothing to push against to get it to reorient itself. So what they actually used was the solar panels. So they oriented them to reflect the sunlight to produce a torque that rotated in the desired direction, and were able to stabilize the spacecraft that way. So there are some interesting examples of this, but typically, because it's a small amount of pressure, we don't notice it. You need to be in an environment where there's no other forces acting on you, like in space, and you need the interaction to occur over a long period of time for these to be noticeable. Okay, so let's go through a few expressions for electric fields and try to describe some of the properties of these electric fields. This is similar to what we did in class last time, but it's worth revisiting again. Just trying to transfer this over to my iPad so we can... Not working. All right, well, let's do this. Let's just describe as much as we can without writing it down. Find the frequency, wavelength, period, amplitude, velocity, direction of motion, polarization, and expression for the magnetic field. That's a lot of stuff. Let's find the frequency of these waves. This first wave, the frequency we're going to get from the term in front of the time, right? The factor in front of time is omega. And in this case, for wave 1, omega is going to be this 2 pi that's out here times this 3 times 10 to the 14. That whole thing is omega. The frequency is omega over 2 pi, which means 3 times 10 to the 14 is the frequency of this wave. What about for wave 2? How are we going to get the frequency of this wave? So remember, omega is the term in front of time, so we have to take this and divide it by 2 pi. We didn't have to divide this by 2 pi because we also had to multiply it by 2 pi here. Okay, so we've written these waves in different forms, and that affects how we work out the frequency. The wavelength. So for this first one, we know that when we increase by 1 wavelength, the argument has to increase by 2 pi. So that, because we've got this factor of 2 pi here, this product, when it increases by 1, will cause the entire argument to increase by 2 pi. So evidently, the wavelength must be 1 over 2 times 10 to the 6 meters, which would be 500 nanometers, if you work that out. Down here, what we have is the product of 0.7 times x times 1 wavelength has to equal 2 pi. So the wavelength for wave 2, we're going to get by taking 0.7 times the wavelength and setting it equal to 2 pi and solving for the wavelength. So it's 2 pi over 0.7. How can we get the period of the wave? The time it takes for 1 full cycle. Hedya? Yeah, we already worked out the frequency, and the frequency is 1 over the period. Right, so those are inverses. So if we've already worked this out, just take the inverse. Alternatively, we could say how much does this need to increase, the time, so that this argument increases by 2 pi, and that will give us the same result. The amplitude. The amplitude is the term in front of the sinusoidal oscillation. So 4 volts per meter for the first wave and 0.4 volts per meter for the second wave. Yeah. Can we assume these are all moving at the speed of light? So no. We're about to calculate the velocity. And let's work that out. So I am going to switch over. I'm just going to have to rewrite these expressions. So E1, we'll just work with this one, was 4 volts per meter times sine of 2 pi times 2 times 10 to the 6 x minus 3 times 10 to the 14 t, all polarized along z. So if we want to work out the velocity of this, there are several ways to do this. Velocity is omega over k, which is equivalent to saying velocity, if omega is 2 pi over the period, and k is 2 pi over the wavelength, those 2 pi's cancel. This is the wavelength over the period, or the wavelength times the frequency. Okay, so the wavelength, we said, was 1 over this. So that's 0.5 times 10 to the minus 6 meters, or 500 nanometers. And the frequency is 3 to 10 to the 14 hertz. We got it from that right there. We said that 2 pi times this was omega. And we divide that by 2 pi, we're left with the frequency. So that was the frequency. So with this, we can just write the velocity as the product of these two. So 0.5 times 10 to the minus 6 meters times 3 times 10 to the 14 hertz, which is cycles per second. So you can see we're going to get some number of meters per second. And we have 0.5 times 3, so that's 1.5. And 10 to the minus 6 times 10 to the 14 is 10 to the 8th. So this is not traveling at 3 times 10 to the 8 meters per second, which is the speed of light in vacuum, which suggests this is not traveling in vacuum. Let's see if we can get an expression for the magnetic field of this wave. So the magnetic field has an amplitude that's E over V. And the direction of the magnetic field we can get from the cross product having to equal the direction of the E cross B will give us the direction of propagation, which I can now write as the direction of the Poynting vector. And I know that it's propagating in the x direction here, because these terms have opposite sign. So as time increases, this term is going to get more negative. So this one has to get more positive to follow a point on the wave. So it must be propagating in the plus x direction. Okay, so we know it's propagating in the x direction. It's polarized. The electric field is polarized in the z direction. So we have to figure out what z cross something, the direction of the magnetic field, will give us propagation along x. So if x is to the right, y is pointing up, and z is out of the page, we want to do z cross something equals x. So z, the first vector, we point our fingers of our right hand in that direction. We're going to curl them in a certain direction that we don't know yet, and it will leave our thumb pointing along x. So we have to point our thumb along x. We have to start with our fingers along z. So when we curl them, our fingers are pointing down, which is the minus y direction. So we know the magnetic field has to point in the minus y direction. So writing the magnetic field as a vector, I can just take this expression for the electric field, divide it by the speed that I just calculated, right there. That is a fraction. And give it a direction of minus y hat. And that's an expression then for the magnetic field of my wave. I can do something similar for the second wave. I'm not going to go through all of it, but let's ask a couple of interesting questions here. What direction is this second wave propagating? Yep. It's in the negative x direction. So as time increases, this term gets more and more positive. So this term would have to get more and more negative to follow a point on the wave. So x would have to be, it has to go in the negative x direction. Whenever these terms have the same sign, it propagates in the negative direction of whatever coordinate this is. So it's in the negative x direction. So that's going to affect the direction of the magnetic field. And yeah, the speed, we'll get it from omega over k. Here's omega, and here's k, 0.7. We'll take that ratio. 3.5 over 0.7 is 5. So 5 times 10 to the 7 is the speed of this wave. Yes? Sure. For which one? Any of them. Okay, yeah. So let me write one of these. The second one looked like 0.4 volts per meter times sine of 0.7 x plus 3.5 times 10 to the 7 t in the j hat direction. Okay, so if we want to find the wavelength is the distance we need to propagate for the wave to repeat itself. So distance is this x in this case. So what we need is we need this term to increase by 2 pi when x increases by lambda. That is to say we need 0.7 times lambda to equal 2 pi. And if that's the case, then when x increases by a wavelength, this product will increase by 2 pi. So solve for the wavelength. Lambda is 2 pi over 0.7. Another way of saying that is the factor in front of the x term is k. It's called k. And k is 2 pi over the wavelength. So if we set k equal to 0.7 and solve for the wavelength, we're getting the same thing. So whether you just sort of memorize this formula or whether you think about the meaning of a wavelength as increasing the argument by 2 pi, we'll arrive at the same result. Okay, so we tend to categorize different electromagnetic waves with different names based on their frequency. Magnetic waves that obey Maxwell's equations. So from the longest wavelengths, we have things that we call radio waves. These have wavelengths that are hundreds of meters. As a little hint, when you see an antenna that's optimized for radiating a particular frequency of wave, that antenna is usually some fraction of a wave, usually a quarter wavelength. So if you see a large antenna in the hills, it looks like a radio antenna. It might be 100 meters tall. These are the big, usually red and white towers. that you see. You see them near airports. You see them out in the a little bit away from the city, broadcasting radio waves. Sutro Tower in San Francisco is another example. Um, so radio waves, TV waves as well, although we don't call them TV waves, we call them radio waves, have wavelengths that are hundreds of meters long. And their frequency, we know what their frequency is because that's the frequency that we tune in our radio to. So 105.3 megahertz, 650 kilohertz. If you tune AM 650, that's 650 kilohertz. If you tune to FM 105.3, that's 105.3 megahertz. So those are the frequencies associated with those wavelengths. Shorter wavelengths, things on the order of a few inches or tens of centimeters, we call microwaves. So microwaves are familiar from your microwave oven. The size of the wavelength is on the scale of the stuff you put into the microwave. Another example of something that radiates at microwaves, 2.4 gigahertz, that's your Wi-Fi antennas in your Wi-Fi systems. There's also 5 gigahertz. Those are microwaves. So the size of a Wi-Fi antenna, usually they're sort of folded up onto a circuit board, but if you sometimes see like an external antenna on your Wi-Fi router or something, that gives you an idea of what the wavelength is. It's on the order of a few tens of centimeters. So we call those microwaves. And then as the wavelength gets shorter, we start to call it infrared radiation. So infrared radiation is anywhere from millimeter waves all the way down to micron. Okay, so some of that infrared, we tend to think of this as like heat. Those are the wavelengths that we feel on our skin as being warm. So when you step out into the sunlight, you can see, but you also feel warm. And the warmth you feel on your skin comes not from the optical light from the sun, but from the infrared radiation. And then we have the visible. So the visible spectrum ranges from about 700 nanometers to about 400 nanometers in length. And those frequencies are about 10 to the 14 hertz. So they're very fast. I mentioned that we can see best in the center of this. Our eye's most sensitive in the center of the visible spectrum. And so exactly what the edge of the visible spectrum is a little bit subjective. If it's not an immediate fall off, but just to give you an example, I work with infrared lasers, typically pumped at 808 nanometers, which is considered near infrared. It's not in the visible spectrum. But if I'm in a dark room and I have a very intense laser, I can actually see it. So even though it's not considered visible, with enough intensity, the eye still has some sensitivity there. So what differentiates visible light from these other lower frequency, longer wavelength sources is that the very high frequency of visible light is so high that if we have like an electron in a wire or an antenna, with something like a radio wave that's oscillating several thousand times per second, that electric field can actually move the electron back and forth because the electric field exerts a force on a free charge. And that causes the electron to move back and forth in a wire that produces current. That's what an antenna is. So a radio antenna has current induced in it by the passing radio wave. You can't do that same thing with visible light because the frequencies are so high that the mass of the electron prevents it, its inertia prevents it from moving back and forth fast enough. It can't move back and forth at 10 to the 14 hertz. So we don't see the actual field oscillating up and down the way we can with radio or microwaves. All we can see is the average energy deposited, which is why we typically, for optical visible light, we care about the irradiance, or the power per unit area, not the electric field magnitude, because we can't actually track the electric field the way we can at lower frequencies. And then there's these higher frequency things. Ultraviolet, we know this from like sunburn. These are higher frequency waves. X-rays, likewise, are higher frequency, shorter wavelength. These tend to be able to penetrate further through things. So, we're familiar with this from like the doctor's X-rays, all the way up to like gamma rays, which come from supernova and astrophysical sources that are passing through the Earth all the time. And because they're so high in frequency, and they're so short in wavelength, they really don't interact well with matter. So typically the interaction of a wave with some material works best when the material size is similar to the size of a wavelength, which is roughly why your antennas are on the scale of a wavelength. But what it means is if you have atoms that are like 10 to the minus 10 meters in diameter, and then you have a gamma ray that's something like 10 to the minus 14 meters, it's so much smaller than the atom that it just passes through. So we have gamma rays passing through us all the time, and essentially they don't interact with us, so they don't cause us any issues. All of these are electromagnetic waves. They behave the same way in terms of Maxwell's equations. We just give them different names based on sort of how we use them and the technologies associated with them, but fundamentally, they're all the same thing. So what I want to kind of do is give an example where we can work out some of the things that we just discussed, irradiance, speed of light, things like that, but also is a relevant technology and one that bridges from Physics 51 into Physics 122, modern physics, which I mentioned the other day when we talked about, or I didn't really go into the details, but I mentioned the speed of light is constant. That's called relativity, and gives rise to some interesting things like time dilation. So as another example that advertises that, let's think about GPS. GPS we use on our phones or on our satellite navigation systems to know where we are on the Earth. And basically the way these work is we have these satellites in orbit that are about 20,000 kilometers high and emit about 25 watts of electromagnetic radiation from their antennas at a frequency of about 1575 megahertz. So this particular wavelength, so 1.5 gigahertz, is going to give rise to wavelengths that are on the order of a centimeter, which is very convenient if you want to have a cell phone or something detect these, because you can have a little 1 centimeter antenna inside your cell phone. If this was a much lower frequency, you would need a much longer antenna, right? And so if this were in the kilohertz, you would need, you know, meters, hundreds of meters of wire hanging off your cell phone in order to detect that. So this radiation is broadcast, we'll assume, in a hemispherical beam shape. So it's radiated towards the Earth, not away, so all this 25 watts, but it's spread out over a hemisphere. So the first thing we could ask is, like, what is the irradiance of this wave at the ground? So I've actually worked this out. The irradiance is the total power divided by the area over which the wave is spread. And we're given the power being emitted is 25 watts. But it's spreading out over a hemisphere that's going to have a radius of about 20,000 kilometers. So the surface area of a sphere is 4 pi r squared. A hemisphere is going to be half that, so 2 pi r squared. So with that radius, we get a hemispherical surface area of 2.5 times 10 to the 15 meters squared. So this 25 watts is being spread out over a huge area. So the intensity is only 25 watts over 2.5 times 10 to the 15. That's going to be 25 over 2.5 is 10. And 1 over 10 to the 15 is a femto. So this is 10 femtowatts per meter squared. So that's a very small amount. You're not going to use this to power anything, but you can detect it. Yeah, Gordon? The irradiance does not take into account the frequency. That is correct. What would take into account the frequency is the flux of photons, so the number of particles arriving per unit area. The energy per unit photon is frequency dependent. But I will not say anything more about that. That's a topic for another, for Physics 122. Okay, what is the wavelength of the radiation? I mentioned it's going to be small, on the order of a centimeter, and we can work it out from this frequency. We know that the speed of light is wavelength times frequency, and if it's traveling in vacuum with a speed of c, we can work out the wavelength from c over f. So we have 3 times 10 to the 8 meters per second divided by a frequency of, I think I said 1575 megahertz. Mega is 10 to the 6, and hertz is cycles per second. So you can see the seconds are going to cancel, and we'll get some number of meters. And when I work that out, I get 0.19 meters. Okay, so 19 centimeters. So this is Physics 51 stuff that we can understand based on Chapter 16. The way that this system of locating your position works is you have this constellation of satellites that are basically just broadcasting where they are and what time it is. And that's the signal that you're detecting. And when your phone detects the signal from at least 3 satellites, it knows, it receives them at different times based on how far away they are. The satellite that's closest to you, you'll receive the signal from that earlier than you would receive the signal from a more distant satellite. So you get these signals that say, okay, this satellite was over there at this time, this satellite was over there at this time, this satellite was over there at this time. And based on when you receive the signal, you can work out how far away the satellite is. And you know where it is because it tells you that. So you know that you must be in a sphere centered on that satellite with a radius given by the distance that the light traveled from when it sent the signal until when you received the signal. And because it tells you when it sent the signal, and you have a very accurate clock in your GPS receiver, you know when you receive it, you can work out how far away you are. But you don't know where on this circle you are. But if you also have a circle of locations you can be centered around another satellite and another satellite, those circles will intersect at a point, right? And that's your location. Okay, so if the clocks that are used on these consumer level GPS receivers have an accuracy of about 10 nanoseconds, and the satellites themselves have a clock with an accuracy of about 1 nanosecond, then we can sort of ignore the uncertainty in the clock and the satellite, and the uncertainty in our position is going to be determined by the uncertainty in this time. So we can ask, how accurately can we be positioned given the uncertainty in our clock on our device? And so we're going to use basically distance is velocity times time. And if our uncertainty in our time is 10 nanoseconds, and our speed is 3 times 10 to the 8 meters per second, then that's going to give us an uncertainty in distance of 3 times 10 to the minus 9, times 8 and minus 9, 3 times 10 to the, let me rewrite this, 30, 3 times 10 is 30, 10 to the 8 times 10 to the minus 9 is 10 to the minus 1 meters, or 3 meters. So having a 10 nanosecond accuracy on your phone's clock allows your phone's GPS to locate it to within about 3 meters, right? And that's about what we see. So the reason that we want more accurate clocks is to get more accurate navigation. Now, something interesting happens when you have things moving very fast. We mentioned there was time dilation last time, which is a topic that's beyond this class, but the satellites are moving very fast, and because of that, they run slow by about 45 microseconds per day relative to a clock on Earth because of the time dilation. The gravitational field that they feel is also weaker, which causes them to move faster than clocks on Earth by about 7 microseconds per day. This idea of clocks moving at different speeds and different gravitational fields is illustrated very well in the movie Interstellar. And when we combine these two relativistic effects, the clocks in this GPS satellites tick at about 38 microseconds per day faster than they would on the ground, purely because of these relativistic effects that if you're interested in, you can take Physics 122 to learn more about. So the question becomes, if we don't account for this relativistic effect, if we just use the physics that we had learned prior to 1904, when Einstein introduced relativity, how accurate would GPS be? And so if we're losing 38 microseconds per day, then when we go back to this calculation we did, every day, if our time changes by 38 microseconds, that's equivalent to changing where we think we are on the Earth by 38 microseconds times c, which works out to about 11 kilometers. So your location would be off, would drift by about 11 kilometers per day. Right, so after a week, your GPS would think you were in LA when you were up here. So that's just kind of interesting, because that's the sort of practical example of relativity, which is mostly like these weird like theoretical ideas of like what would happen if you travel near the speed of light. But there's actually practical applications of it that we use every day with the GPS. Okay, so I want to give you a chance to work out some questions involving these. So if the LAs will pass out the group work questionnaires. There's a series of 6 multiple choice questions that I'd like you to work through with your neighbors. So take about 10 minutes to do that, and then we'll go over the answers together. Oh, and while they're passing that out, I have a little demo I want to do that is kind of fun. I've got here a Tesla coil, which will produce high frequency, high voltage. And because it's at very high frequency, it will actually propagate as an electromagnetic wave propagating out. And what I can do is I can use that to light up this light bulb. So I'm going to dim the lights and turn on my Tesla coil. And without touching it, that electromagnetic radiation propagates to the light bulb and will excite the fluorescing molecules in the light bulb. So lightsabers right there. Okay, so let's just go over the answers together, and this will take up the rest of our time, which means the quiz will be on Thursday. Okay, so the first one, we have the given electromagnetic fields, and we know what they're at a certain point, E is in the negative x direction. They're propagating in the positive z direction. We know E cross B has to give us the direction of propagation. So we need negative x cross the magnetic field to give us positive z. And that's going to happen with choice B. So we should get the magnetic field in the negative y direction. Question 2, we know the direction of the electric field is along x, and we know it's propagating in the minus y direction because these terms have the same sign, so it must be in the negative direction for whatever that is. So it's got to be, so it can't be A or B. Whoops, it can't be A or B. And then the magnetic field has only a z component. Oh yeah, so we can get the propagation is in the minus y direction from x cross minus y is going to give us, sorry, it propagates, so the direction is in minus y. Okay, so it can't be C. And then finally, is it true that the magnetic field has only a z component? Well, if the electric field has only an x component, and it's propagating along y, we need the electric field cross the magnetic field to give us the y direction. So electric field, magnetic field in the y direction all have to be mutually perpendicular. So yes, the magnetic field has to be along Z. The electric field is along X. Propagation is along Y. So that gives us, that confirms that D is correct. Question 3. The magnetic energy is going to be the greatest whenever the magnetic field is the greatest. And the magnetic field is going to be the greatest wherever the electric field is the greatest, because they're proportional. Question 4, where does the Poynting vector have the largest magnitude? Well, remember the Poynting vector is 1 over mu E cross H, or E cross B, I'm sorry. So its magnitude is going to be proportional to the magnitude of E and the magnitude of B. So that's going to be greatest wherever E and B are the greatest. So that's going to occur here at the origin. It's going to occur here half a wavelength later. And it's going to occur here at the end, 1 wavelength away from the origin, which gives us choice D. Question 5 shows this weird electric and magnetic fields that are out of phase. We said in a traveling wave they're proportional, but this represents what's called a standing wave. It's the sum of a forwards and backwards going wave. If you reflect light off of a mirror, for example, you get this. And we know that a conductor, like a mirror, the electric field in that conductor is 0. So our incoming electric field and our outgoing electric field have to cancel each other out. So that's why the electric field will flip over and always start from 0. But the magnetic fields will add. In any event, we get what's called a standing wave here. And the average Poynting vector in this wave, the Poynting vector is E cross B. And there are regions where E cross B is going to point to the right, like right here. And there are regions where it's going to point to the left, like right here. So it's going to average to 0. Okay, and if we recognize that this comes from a forwards and a backwards going wave, then it makes sense. Because one has a backwards going Poynting vector, one has a forwards going Poynting vector, and they add up to 0. And then finally, for this spectrum, what can we say? Well, red light has a greater wavelength than violet light. So this doesn't talk about wavelength, it talks about frequency. But a longer wavelength means a shorter frequency or a smaller frequency. So red light has a smaller frequency. So it could be C or D. It can't be A or B. And then the second part of the question talks about the speed at which the red light moves relative to violet light. But this is in a vacuum. The speed is constant. It doesn't depend on wavelength. So it can't be either of these. And that just leaves us E, none of the above. Okay, so we'll wrap up there. Next time we'll have our quiz, and then we're going to do review. The review, the way that's going to work is you're going to separate out into groups based on which chapters you want to review. And then you're going to review the quizzes from those chapters. So please take a moment to look at the grade book and figure out what are the 3 lowest quiz grades you've gotten, so that that can dictate sort of what chapters you review on Thursday.